junk here? Not yet? Nope. There he is. So the planetarium is empty, I assume now?
Yes.
Okay, good.
Unless somebody's hiding under the seat.
Yeah.
No. So the meeting is now officially underway. And Tom, you were going to show slides? Oh, yes. I know you send these things out beforehand, but I frequently don't read them. Thank you, Chuck. So what was the planetarium show about?
About
30
minutes or so. What, Chuck? What was it about? Fumbling. Fumbling, yeah. I was trying to do a bunch of galaxy images, but a bunch of them weren't present on the system and needed to be downloaded from the web, and it wasn't successfully doing it. So it was
Okay.
It was so good.
Yeah.
It was fun.
I'm sure it was. Okay. So we have advertising our blogcast. Never know what that's called. Vlogcast, video log, on Mondays, 11 to 12. And we are on there live, and you can watch us live. And if you figure out how to, you can call in and ask us questions. Only a few have figured that out and done it successfully. But most people watch it later. And I think we're up to 260 subscribers. So it's a lot of fun doing it. I write the talking points so everybody has a backup to talk about. But at the meeting, we talk about whatever comes up so we can ramble. But we stick to astronomy and science. Tuesday, we run a workshop online on Zoom from 7:30 to 9. It started out, as many of you know, as a workshop for fabricated mirrors and optical elements over here in Broder Hall. But because of COVID, we went to Zoom, and then we had so many people join the workshop that can't get here by car, so we just stayed on the Zoom channel. And right now we're doing mostly, one person's building a telescope, and we do mostly images and processing. The bottom thing was one more thing I had. Oh yeah, no, okay. Go ahead. Now, Pat is our merge manager, Pat McPartland. She's not here tonight. She has had surgery, and she's doing fine, but she needs to stay home and rest. We are, go back. So we are getting out of the business, so if you want one of these coveted cups here, now is your chance to get it. We have a few left. We are out of most of the common sought-after shirt sizes, but there are some things left. We can arrange, if there's a big demand for things, we can arrange to do a bulk order in the future. So make your comments. If you're all dying to have a sweatshirt with a zipper in the front, let us know. And the summer picnic potluck. We're not having a meeting next month in June, the first Friday night of Zoom. That is our club picnic potluck. We used to, for some reason, we were associated with the City College, and we had academic hours, that is, we disbanded in the summer for 3 months, but I couldn't figure out why we were stopping to do something that we enjoyed doing because of the summer. So we kept going through that, but we kept the picnic potluck as a salute to that off time. So if you want to come, bring something to eat. I'm going to bring chicken enchiladas. They seem to go pretty well. We're going to meet in here, so we're going to eat in here. They'll have tables set up. Now I'm not going to ad-lib it for this. This is our outreach coordinator. outreach is the primary function of our club. And I saw Chuck come in. Go.
Lots of propaganda here. If you're into papers, star maps, moon maps, goodies like that. Thank you, Jerry. Okay, totally quiet month. There are some school events, but they're all kind of during daytime. They're calling them science nights, but they're during daytime, so really not a public thing. But as far as the public events, second Saturday here at the museum, we'll have our star party starting at 8:30 to 10, so kind of quick and dirty. Hopefully it'll be clear. And then third Friday at Westmont on the 15th, Friday the 15th. And then third Tuesday, the 19th, at Community Rail Marketplace, the big box. And just to fill in for Pat, for the merchandise, you can also go directly to ID Works if you want, and order it there. And their web page is up there. It'll be more expensive, you know, because it's a one-off run if you order one, but you can still get it that way if you just absolutely have to have something. And I guess that's it. So thanks.
Okay, now Tom is our equipment manager, and he stores all the stuff in his house. And yeah, Art Harris stores it at his place too. So he has a number of things for sale here. If anyone's interested in it, these are things that donate to our club, and we either use it or we sell it. Do you want to say anything about this?
We do have some free 12-inch telescopes that will be for sale, and got a couple 8 inches, and there's some that need repair. We're going to do some repairs. There's the black tube on the right that's called the Dobsonian Newtonian type telescope that Gale there was standing next to it. He made that telescope. We're going to make a base for that. And we did sell the one that he's holding on to one of our members, so that's gone along for the mountain bottom. But we do have lots of eyepieces available, sets of eyepieces and other odds and ends, so let me know if you need something. We do have smaller telescopes like 5 inch as well, a couple 5 inches. They're in good condition. So let me know if you're looking for something that can actually zoom in on Jupiter or Saturn. All right.
Okay.
Don't know what to say about the directory.
We're all out of those anyway.
Okay.
List of folks, and then Rodney's turn.
Yes, we have Palmer Observatory, which is out by the butterfly thing here, is open at least, let's see, second Saturday, second Sunday, May 10th. It's every Sunday from 1 o'clock to 3 o'clock for solar viewing. We have some excellent solar telescopes out there. Hydrogen alpha that lets you look at the prominences. As you know, the sun is mostly made out of hydrogen, so if anything is happening on the sun, you're going to see it in hydrogen alpha light. We have 2 hydrogen telescopes that show the prominences, and then we have a couple of white light telescopes that just look at the sun and see the sunspots. How many people do we get at a time? 200 in that 2-hour period typically. It's quite nice. So, yeah, okay. The vice president is the one that arranges our speaker program. And he's going to introduce tonight's speaker. And before you ask, there's several thousand people at JPL, and she does not know Martin Cakin.
Not exactly like our club, probably.
No, where I was at 1,500 people, people would say, "Oh, you're at Santa Barbara Research Center," and I'd go, "Yeah," and I'd say, "Do you know so-and-so?" Never.
You notice you will notice, she looks exactly like her picture. We get these people that come in and the picture, they sent us 20 years ago. It's like one of those dating sites. Well, thank you, Mr. President, for a bonus in your check. You're doing a great job. Good to keep you. I'll try to keep this short, too. Dr. Abigail is here. She made it up from Pasadena in record time. She used their mock-up rover, It's pretty good mileage, but damn, the price was crazy on the gasoline when it double parked outside. This woman has some vacation pictures you're not going to believe tonight. You'll see. And I guess all those rovers take selfies, don't they? Nevertheless, it's called Snapshots from Curiosity, our Martian mountaineer. This sucker for 13 years has been climbing the Mons. That's what they call them. It's not Olympus, though, is it? That's a 15-mile-high Mons. That's an inactive volcano. I like to do a couple things before I introduce her. One of the things we like to find out as a club, since this is, ladies and gentlemen, our official meeting, always first Friday, is who are our special guests? Who are the possible future members of Santa Barbara Astronomical Unit? So I'm going to ask you now to be totally honest, and we're going to welcome you later on by meeting you and greeting you. Raise your hand if this is your first visit here to one of our meetings. Keep it high. All right, give it a hand. Now raise your hand if you've been here before, but you're not a member of the club. If you've come before, aha, we did something right. You're back. Members of SBAU, there you go. These are the guys that are going to take the rest of you to drinks later. Buy you a meal. It only costs, you know, about what a meal costs to join our club, $20. In any event, that's how I learned. Let me run down some of the future coming attractions and put out an appeal on August because I could use some help. Next month, as the president said, now this is a good reason to join our club. If you make a dynamite salad, or you have a killer type of a food, what is the word? Killer casserole. Reagan, we're going to be in here, of all places, this dinky little clubhouse they give us, where we're going to have our big meal of the year next month. That'll be on Friday the 12th, incidentally. So no speaker, but Friday, July 3rd, midsummer, Dr. Gerardo Aldana of UCSB, who is the chair of their Chicano Studies Department and an expert on Mayan ancient culture, is going to do an incredible program, just like Abigail does on Mars rovers. His is about ancient Mayan astronomy. They somehow track the stars. I lost Dr. Howard Wee, I've been telling you about, for August 7th. He suddenly got involved with a big Caltech symposium, and so I moved him to November. So I could use any help, any suggestions. I must have sent out a dozen feeler Gmails, and not one of them has been replied to. Tried to hit USC. I don't think we've ever had a USC speaker here. We just had a UCLA a month ago. Abigail will be our second JPL. They're always good about sending incredible people. We've had Caltech. In fact, that was Dr. Wee, and he came here last November for Dr. Corngut, the Spherex guy. And so I was looking forward to seeing Dr. Corngut again in August. But right now, August is unbookable. It must be like May. May is hard to do because it's going into summer and they're all planning their big vacation, their holiday. But I somehow got Abigail, and we're very lucky. And now August may be the same thing. They're coming back. Perhaps some of our members could tell us how that is. For example, Sean Kelly, who runs the City College Astronomy Department, is right here, ladies and gentlemen. This man is awesome. And for the members only, we may have a big surprise in October. I can't tell you yet, but you got to join the club to know what it is. If you know your names in astronomy, then you're going to want to be part of this. So what am I missing? I guess I'm done. I'll always go to Ralph's and pick up their chicken. That's what I bring to the big potluck. Nobody knows. I tell them I made it in my backyard. Okay, Dr. Abigail is ready to show us her vacation pictures. She is, ladies and gentlemen, a planetary scientist at NASA's Jet Propulsion Laboratory, is currently the Deputy Project Scientist for the Curiosity Mars rover mission, which I believe has been up there 13 years. I could be wrong claiming. Her research focuses on understanding the geology history of rocky planets in our solar system through the tools of remote sensing. Dr. Abby is also developing instruments, get this, for future flights to our moon to search for water. And as a participant in the Japanese Space Agency's upcoming mission to bring a sample back from Mars's moon Phobos. Wow, how are you going to do that? The woman majored in geology and physics at Yale, received her PhD in planetary science from Washington University in St. Louis. And you might want to start coming up here now, Abigail. She enjoys backpacking, photography, travel in her free time, and she is quite a climber herself. Then Dr. Abigail Fraeman. Let me do this here for you. It doesn't fit this month, all right. Q&A later. Or any time if you want to talk.
Well, wonderful. Thank you so much for that nice introduction, and thank you so much for inviting me to come speak with you, and thank you all so much for coming and spending your Friday night here at the museum and here to listen about what we've been doing with our Mars rover Curiosity that has been on the surface of Mars for 13 years. I always like to start with where are we right now. So literally this morning, I was at JPL planning what we're going to do with the rover, and this is the view looking behind the rover. You can see that kind of trash can looking thing in the middle. That's not actually a trash can, that's a chunk of the rover. That's our ultra high frequency antenna. That's what we use to talk to the orbiters and send the data back to Earth. As alluded to in the title, we are climbing a mountain that I will show you soon. And so here we are on the flank of the mountain. We're looking down into a crater. And what looks like a mountain range way in the distance, it's a little hard to see because we're in the dusty time of year on Mars. That's actually the rim of the crater. You could almost imagine that we're here on Earth, maybe somewhere in the desert. I love Mars because I think it looks very Earth-like, but it also looks very different. And hopefully I'll convince you of that. That was our picture from today, but this was the picture that we saw when we first landed back in August of 2012. This is taken by a camera that's underneath the belly of Curiosity right after we landed. It was immediately after we landed. Curiosity landed with this crazy contraption called a sky crane, where it hit the top of the Martian atmosphere going 13,000 miles per hour, big parachute open, retro rockets fired, and then it was lowered on this tether gently onto the surface of the ground. And we got a whole bunch of dirt and dust on the camera from those rockets firing and placing us down. But we were able to pop that dust cover off, and this was our view. You can see the shadow of the rover looming on the ground. And here in the background, this is our mountain. This is a mountain called Mount Sharp. This is what an orbital view looks like. Curiosity actually landed in this big crater. It's called Gale Crater. It's about 150 kilometers across. I don't know what that is in miles, but you guys can convert. But it's located right near the equator of Mars. And why we chose to land in this crater and why it's so interesting is because it has this big mound of material in the middle. It's informally named Mount Sharp. This mound is about 5 kilometers tall, or 3 miles. So it's about the same height as the Grand Canyon is deep. And from orbit, we can actually see that the mountain is composed of many different layers of rock. And so we could hypothesize that this was actually sedimentary rock that had been brought into the crater by wind or water, turned to stone, We could see that the textures and the composition of the layers were different as you went up the mountain. And so the idea was these layers record a history, like a textbook of the Martian environment that was present when they formed. And by landing at the base of the mountain, we'd be able to work and climb our way up and read the history of Mars layer by layer, much like you would do climbing up the Grand Canyon. This is an even better picture after landing, not from our hazard cameras, those black and white cameras under the rover, but here we are now with our color mast camera located about 2 meters off the ground on the rover's mast, pretty tall. But here you can see Mount Sharp looming in the distance. These features here, these are we call them the scour marks that were made by the retro rockets firing into the ground. We couldn't land on the mountain itself, it's too steep, too treacherous, so instead we landed in a nice flat spot in the plains. And we can take our camera lens. We have 2 cameras, a 34 and 100 millimeter camera, so we can zoom in with our telephoto 100 millimeter camera, and this is what we see on the mountain. And just like we saw from orbit, we can start to see just layers and layers and layers and layers, and this textbook of Martian history that probably covers tens of millions, if not hundreds of millions of years that we're going to be able to read, maybe even billions of years, we're not sure. There might be gaps in time from when the layers were deposited. I'll just put some units on there for you to see. Here are the crater plains that we land on. There's this big field of dunes that we had to navigate around before we could actually start climbing the mountains. On Mars, the sand is actually black instead of the white colored sand here on Earth. That's because on Mars, all of the sand is made up of broken bits of lava rock. So if you ever have the opportunity to go to a place like Hawaii or Iceland, you can see the black sand beaches. Same story on Mars. So it's these big fields of black sand. And then climbing up, we had all of these different layers that from orbit, we could actually get a sense of what their composition would be using visible near-infrared spectroscopy. We can look at wavelengths of light reflected from the surface of Mars, and when we see absorptions in different visible and near-infrared wavelengths, we can tell the kind of minerals that are present. So this was a layer here that we saw was enriched in an iron oxide mineral called hematite. Higher up, there was a unit that had lots and lots of clays, which tend to form in watery environments that has water. That's the kind of water you might want to drink. It's also very good at preserving all sorts of chemistries. And then higher up, we see a transition to salts, in particular sulfate salts, kind of like Epsom salt that you might put in your bath, very similar. And so the thinking before we landed was that we'd be able to see some evidence of Mars going from the wet planet that we know it once was to the dry planet that it is today, and we'd be able to get a hint about how that happened and how the environments on the planet changed. And today, we're there, so we've made some pretty good progress. I should step back a little bit and talk to you, what is Curiosity doing? Why are we going to Mars? And the big question that Curiosity was designed to answer, we started, we talked about Mars, was there water on Mars? You hear that question a lot. Yes, there was water on Mars in the past. There's water on Mars today in the atmosphere, in the rocks, in the poles. You want to jump to the question, was there life on Mars? That's a really hard question to answer. So Curiosity is designed to answer the question that's right in the middle between those two, which is, did Mars ever have a habitable environment? So in addition to water, did it have all sorts of other ingredients that we know life needs in order to potentially originate and certainly to survive? So this includes things like the chemistry that life needs, molecules that have carbon and nitrogen and phosphorus in it. Does it have places where you might be able to get energy? Sometimes you can get chemical reactions that we can see in the rock record that we know can power metabolisms of life. And so these are the kind of questions that Curiosity is designed to answer. Gale Crater is a particularly exciting place, and Mount Sharp to go study these because we know it formed in a period where Mars was going intense environmental change. The Martian geologic timescale, unlike Earth, which has many, many different things we break it into, it's easy on Mars. There's only 3 different periods. The Noachian, which is the oldest period, the Hesperian, kind of middle-aged Mars, and the Amazonian period, which is what we're in today. We think there was this big change that happened from habitable Mars to uninhabitable Mars sometime in probably the mid to late Hesperian. And Gale Crater perfectly records this time period where we think there was a lot of environmental changes happening. And so by landing here, we're going to be able to search for habitable environments early in Mars's history, late Noachian, early Hesperian, all the way through to the end of the Hesperian, and maybe a little bit into the Amazonian. So it's going to give us our best chance to try to see, was Mars habitable, and if so, when? To do that, we have a very capable rover. As I mentioned, the mast is 2 meters tall. Curiosity is basically the size of a golf cart or a Mini Cooper. It's huge. It has 17 different cameras, so I'll show you pictures from some of those. But importantly, it has 10 different science instruments that are designed to interrogate the rocks and the atmosphere to help us get at this question of was Mars ever a habitable planet? All of the instruments are very important. One of the coolest ones, we have a laser on the head of Curiosity that we can fire into rocks, and we can look at the plasma that we create, and we can actually look at the emission lines in the plasma to tell us the elements that are in the rock, kind of like you might look at a star with a spectrometer and see what elements are in the star. We also have, very importantly, on the end of its 70-pound turret, on the end of its arm, a drill that we can use to drill into rocks. We get like a chalk-sized piece of rock, we can powderize it, and then we can put that sample inside the rover, which hosts 2 very special laboratories. One of them can tell us very detailed information about the crystal chemistry of the rocks, what minerals are there and what are their structures. And the other one can detect all sorts of compounds, including what we're really excited to find is carbon-containing compounds or organic molecules. And it's really these 2 instruments. They're our mobile chemistry lab. It's incredible that we can bring them to another planet. And they're the reason this vehicle is so massive. This is a view of our traverse about to date. So as I said, we landed on the plains near the mountain. And ever since, we've been driving. We went to check out the site Yellowknife Bay, which we'll talk about first. But then we had to go all the way around to skirt around this big dune field to get to a place where it was safe enough to cross so we wouldn't get stuck in the sand, and started making our way up this mountain. This morning, we planned sols 4,883 to 4,885. A Martian day is called a sol, and so day 1 on Mars is sol 1, et cetera, et cetera. Curiosity was supposed to go for 2 Earth years or 1 Mars year, so about 600 sols. So we've certainly exceeded the planned lifetime of the vehicle. And we planned 3 days because we want to cover the weekend, so everyone can go home, enjoy their weekend, and we'll come in on Monday and see what happened. We've driven over 36 kilometers or 22 miles, but the really impressive stat is that we've climbed over 930 meters in elevation since our landing site. So that's over 3,000 feet. So this would be quite a hike, I think, if you hiked it here on Earth. I think once we hit 1 kilometer, we're going to have a big party. But it's certainly the largest amount of climbing any rover has ever done on another planet, and it's giving us an opportunity to really interrogate this wonderful sedimentary section. But our first stop will be here, down in Yellowknife Bay. We landed and we actually turned in the opposite direction of the mountain than you think we should go, which was a somewhat puzzling decision to the engineers, but the science team was excited to go the wrong way because we could see from orbit this area called Yellowknife Bay, and from orbit, everything we could tell by looking at the geology, we thought, if there was ever water in the crater, this would be exactly where it would pond. We could see these channels cutting in through the rim of Gale Crater that seemed to terminate in these alluvial fans right near Yellowknife Bay, and we could see that it was the lowest local spot for miles and miles around. So if you wanted to find a lake at the bottom of the crater, here's where you would go. This is what Yellowknife Bay looked like when we got there. You can see the mountain there in the distance, and what we found was indeed, yes, this was once an ancient lake. We were able to look at the textures of the rock and find there were these really fine-grained mudstones that were really finely laminated. And then we were able to look at the composition inside of them. We found a whole bunch of clay minerals that you would expect to form in a lake. And then we were able to drill, and we were able to look at the composition of the kind of chemicals that were trapped in here. And this was one of the really exciting findings, and we found it right after landing, although it took us years and years and years to go through the data and run laboratory experiments to really make sure we had it right. But what we found was a whole bunch of different salts that had things like nitrogen in them and chlorine, these perchlorates and these nitrates. And then we also found right away a whole bunch of these organic molecules. These again are the carbon-containing molecules that we know are one of the building blocks of life. Are these body parts, pieces of life? Maybe, but they could also be molecules that formed through natural geologic processes or molecules that were brought to the surface of Mars by meteor and asteroid impacts. We have since drilled many, many times 52 different samples we've analyzed, and this is a family portrait of Curiosity's drills. I love this picture because it shows how diverse Mars is. We think of Mars as the red planet, but it turns out when you get under the surface and you brush away the dust, Mars is actually the green planet and the purple planet and brown planet. All these different colors, and all these colors are because there's different minerals and different conditions that were present when these particular layers formed. So this is telling us something about the diverse history of this planet through time. We just put out a paper last week, so you may have seen it in the news, a new discovery from one of our drilled samples that we drilled 6 years ago. It took us that long to get through the data and really make sure we knew what was going on, but increased our inventory of the kinds of organic molecules that were present. We found this many hundreds of meters up on the side of the crater in an environment that was still deposited in a lake. This is kind of a family portrait of some of the organic molecules we found, and there's a whole bunch of them. I think some of the most exciting ones include these long-chain hydrocarbons. These were organic molecules that we found in that original drill site. These are exciting because we think they could be the breakdown products of fatty acids, which are essential for life. We've also announced that we just found benzothiophene, which is one of these organic molecules that we know is found in many meteorites. And so this is telling us potentially something about how organic molecules were delivered to Mars. And then we also found nitrogen heterocycles, and these are a precursor to RNA and DNA. So what we're finding is that all of the things that Mars needed for this prebiotic chemistry, all the ingredients that life may have needed to form, were present on the planet, and excitingly, they can be preserved in Mars's rocks for billions and billions of years. So if we're looking for evidence on Mars, for life on Mars, there's definitely a reason to think that even if it's extinct, it can still be preserved. We just need to either send more sophisticated instruments, or even better, bring those rocks back to be able to study here on Earth. So we found lots of stuff in Yellowknife Bay. We climbed up through this lower part of Mount Sharp. What we found was most of all of these rocks were formed in lake environments. It's pretty remarkable. Some of them are lakes, some of them were rivers. But essentially we think because there's such a thick section that was lakes and rivers, they must have been present for probably tens of millions of years. But things started to get a little bit interesting when we reached this area here, where we saw the transition from those clay-bearing materials that we saw from orbit into the magnesium sulfate, or those salty materials. And this is what that looked like on the ground. It's a pretty dramatic view from the rocks in the ground. So down here, all these lake deposit rocks. And as we started to climb up, we saw the rocks looked very different. We can look at the way that the layers are shaped, and we can look at the size of the grains in the layers, and we can tell that these are starting to be deposited in drier environments that are more rivers, or as you keep climbing, some sand dunes and sand sheets. So water is starting to disappear. So just as we predicted from orbit, we could see that the environments on Mars were starting to dry up, and it was starting to become a place that maybe life wouldn't have existed, or would have had a harder time hanging out in. This is a really fun butte we named Mont Mercou. You can see there's a rock sitting here on top. We did some calculations. We got the rover up close to the butte, did some calculations to see will this fall down on the rover or the rock fall down. We think no, but we wanted to make super sure. This is a view again of that same feature, that rock sitting on top, but this is one of my favorite pictures of the mission. This illustrates a phenomenon that we discovered kind of by accident on year 4, I think, of the mission, when we were just kind of looking up at the sky during a certain time of the Martian year, right as the sun set, and we saw these incredible clouds that started to form. These are something called noctilucent clouds. They're clouds that come out right at sunset. And what we found is that there's a very specific window during the Martian year, right around the new year on Mars, that you start to see these features form over Gale Crater. And so the next Mars year that came around, we were ready, and we had a whole observing campaign, and we were able to image them and take lots of pictures. I'm not showing one of the pictures, but we can actually see in some of them actually colors in the clouds that were related to the different grain sizes of the ice that was forming the clouds. And from that, we were able to learn something about the cloud physics of how they formed. So, we're looking at the rocks, but we're also looking a lot at the environment around the rover. Another cool experiment that's hard to illustrate that we were able to do near this butte is looking at the radiation. Curiosity has an instrument on board that is a radiation detector. It is measuring the radiation that you would receive on the surface of Mars every minute of every day, constantly throughout the mission. We've gone through now a full solar cycle since we've been on the surface for 13 years. And this information is hopefully going to help future astronauts understand what kind of environments they'll face. And one of the really cool findings that we found from this radiation detector was when we got up close to buttes like this, we can actually see a noticeable drop-off in the amount of radiation that the rover is receiving. And that's because the terrain is effectively blocking out part of the sky, and that's blocking out part of what you would see. So it can help with modeling and thinking about future astronauts. What kind of structures would they need to build? How thick would they need to be? How big would they need to be in order to build something that would protect you from very harmful doses? This is just another beautiful cloud picture. I love this. This is from a later year, crepuscular rays, and kind of the God ray phenomenon. I think this is the first time we've ever seen that on another planet, and it's just spectacular. So enjoy this picture. This started to be our view as we started to drive up through this salty sulfate-bearing unit, and it's just spectacular. You can see the rover tracks here going through some sand, up and over some sand. This was a particularly narrow pass we had to go through called Paraitapui Pass. And it's a geologist's dream because we can see all of these sections of rocks exposed, and so we can do really careful mapping of the kind of structures that you see here. When you take Geology 101, your professors will take you on a field trip, and what you'll do, instead of looking at the ground, you'll just stop at all of these road cuts. So you can see the cut through the rock and everything exposed. We're effectively getting a Martian road cut through this pass as we drive through here. So that was great fun, and it was great for us to be able to see more and more evidence that this is representing an environment that was definitely drying out. Here's another view of one of those buttes. This is kind of the top of Mount Sharp in the background, but in the foreground here, you can see just all of these layers and layers and layers, and we see things, again, that look like sand dunes, that look like ripples, that look like sand sheets. And so it's telling us all that Mars is drying up, water is becoming less available on the surface. More of that black Martian sand here in the foreground. But water wasn't completely gone. We did see features all littered throughout the rocks at our feet as we drove through this area that looked kind of funky like this. These are kind of golf ball sized nodules, and what we think these are something that actually formed when you had groundwater moving through the rock and preferentially cementing it. And then as you have billions of years of Martian wind blowing and scraping away the rocks, these slightly harder pieces survive. We were interested in checking them out, and good thing, they're not too hard. We were able to drive over them on purpose and bust them open, and then use our instruments on the end of the arm to see what they were made of. And we actually found these nodules were made of these salts that we've been seeing from orbit, these magnesium sulfate salts. And so this gave us a clue, at least in this part of Mars, what was responsible for what we saw from orbit. It's a good example how when you can see from orbit something 18, 20 meters across, you can't really interpret it. You need to get down to the centimeter scale and go, oh, it's these features that probably formed after the rock initially formed, when you had this groundwater moving through, depositing all of these salts. So we'll continue our climb up the mountain, past this transition area, through this feature we're calling Geddes Vallis. There's this big channel that cuts through a huge swath of the mountain, and right in the middle of this Geddes Vallis, there's a channel that has kind of this sinuous shape. I'll give you a zoom in look here for what it looks like. This is the channel it's coming through. You can see it kind of looks like you might expect to see if you had a big river or a debris flow coming through. And so that's what we thought, and we said, you know, we're in this area where Mars is kind of drying out. Why is there this big channel that's cutting through? This is probably one of the last things to form on the mountain. How did that form? And so we went to check that out. Wanted to get up close and personal and see what's going on. Before we did that, as we were parked here, we pointed our cameras uphill, took another picture. This is the view looking up the channel. Just extraordinary view. This is Mars. Like, this is not, when I was growing up, what I thought of when I thought of Mars. I thought of those pictures that you saw from Viking with all of these dark black rocks on these volcanic plains, but this is Mars too. It is a wonderfully diverse planet with so much to explore. But back to our, before I get to the channel, I do want to talk about this one other feature. This is something we call the marker band. This is this kind of dark looking layer that we can trace all the way across the mountain, and it's real weird looking. This is the orbital data view. And we were like, what is that thing? How did it form? Is it an ash layer? What's going on? This is what it looked like when we approached the marker band, and it was totally weird. We were like, what is this? It looks so different. It kind of looks like these like hoi boy lava flows. If you've been to Hawaii, you've seen a lava flow. It's not a lava flow. We're like, there's no volcanoes anywhere. Where would this be coming from? When we looked up close to it, though, we could see it had these very symmetric, ripply patterns off at the side. And this was one of the rare times on the mission where every single sedimentologist looked at this and agreed exactly on what they were looking at. And this is something that's called a symmetric wave ripple. This is what it looks like up top. You can see what it looks like here. And this is a feature that forms when you have shallow water and you have a wind that's blowing back and forth, sloshing back and forth. Kind of like if you're on the shores of the beach, you might look down in the sand and see these ripple patterns. That's exactly what we're seeing on Mars. So what a surprise. After climbing through, we thought Mars had dried up, we lost the lakes, we're in these sandy environments, and all of a sudden, boom, we're in this layer that now shows the lake has returned. This is the first time we can say with certainty the lake was ice-free. Mars was warm enough to not even have an ice-covered lake because there was wind that was clearly blowing the water back and forth. We can calculate, we think the depth of the water was like 3 feet deep. So what an unexpected and remarkable find. But now I'm going to get to this channel, this ridge. This is another orbital view just to give you a sense of scale of this thing. Here's the channel cutting down through the mountain, through this salty unit. This is the scale of our giant rover. It is completely dwarfed by this ridge. And so we were able to get up close to it to look at the material and see how it was distributed, which could give us a sense of how it was transported down the mountain. This is the view what it looks like. It's a little bit less dramatic. Everything on Mars is a little bit foreshortened. But we were able to see it was these very different looking rocks that must have been brought down from much higher on the mountain. We saw they were all jumbled up. We saw different chunks of them, and so what we think this actually was is probably a whole series of different mixtures of dry avalanching coming down Mount Sharp, but also we found some evidence that there was some debris flow, so there would have been water and slurry mixed in, and there were many different episodes of that. And so even late in Mars' history, even after most of the water disappeared, there were still these pulses that would have been coming through to bring this material down the mountain. Here we are, this is our pathway, we're kind of making our way up. We had to find a place where it was safe to actually cross the channel. We did it right here. And this is the view that we saw in our safe crossing area. And oh my God, it was another really weird thing that we'd never seen before. We pulled up to the edge of the channel. The idea was to kind of drive across this way to get to the other side, stay away from the sand, but kind of go across slope here. And we saw this field of like these white rocks, which again were completely new and completely weird and different. So of course we said we have to stop and check these out. Pulled out our hand lens imager, and this is what they look like up close. Completely new. I've been working on this rover and then the Spirit and Opportunity rovers, Mars, for almost 20 years. I've never seen anything like this. You can't see any grains, any other features. We like to break things open with our wheels. I showed you that before, so we did that. We drove over it and broke it open, and you can see on the inside, in the non-weathered fresh surface, it has kind of this yellowish, greenish texture. Here's what it looks up close with our hand lens. You can see kind of these crystal faces. And when we put the arm down and looked at the chemistry, it was just completely surprising. The data came down, and it turned out these are pure sulfur. which we saw these sulfate salts, but we've never seen pure chunks of sulfur. They're totally perplexing. On Earth, you can get pure sulfur forming a lot of times in like hot spring fumarole environments. This is not a hot spring fumarole environment. We don't see any other high temperature minerals that would make us think that. You can have them form at springs sometimes, but usually there you have microbes there that are helping the sulfur to form. It's not really the default hypothesis we have here, so we're still kind of scratching our heads. We're hoping we'll see it again. Hopefully if we see it again, it will provide more clues, but so far the only place we've seen it is in the middle of this channel. So, really weird, really cool. We have some kind of exotic ideas with like groundwater chemistry and clathrates around the sulfur that may have formed it, but I'm really hoping we see it again. You know, this may have been brought from higher on the mountain, so maybe as we climb higher, we'll see it. This is just a nice video, I hope it plays. Showing a day on Mars. This is as we were parked in a single place. We took a whole bunch of images with our hazard camera underneath the belly of the rover, and you can see the shadow of the rover moving across as the sun moves across the sky. Again, I like it because it shows Mars. It's this alien place where you find like chunks of sulfur, but it also looks very Earth-like when you can see things like the behavior of your shadow on this 25-hour day that's very close to our 24-hour day. All right, so I'll wrap up about where we are today and what we just finished up, which is this area called the boxwork. Here is a picture snapped from one of our orbiters this past February as we were making our way up through all of these sulfate layers towards the boxwork, and if you look really carefully, that's where our rover is. If you look, you can see the little tracks coming through. This is 25 centimeter per pixel imaging. And it was really cool. We realized this, we think it's the first time we've done this. We've taken a few pictures of the rover from space before, but we were actually in the middle of a drive at the same time this image was taken. So the rover was driving while this was taken. We were clearly going slow enough that it's not like a big blur. That would have been awesome. But we were on the move, and we were being looked at from above. But this is an oblique orbiter view of what we just investigated. EM5 is our 5th extended mission. You know, the original mission was 2 years, and so every 2 to 3 years we have to repropose to NASA why the science is so compelling and we should keep going. So we're in the 5th extended mission. We're exploring this area that from orbit looks like these weird web, we call it kind of a spider web looking terrain. This is another feature that we can map a really long way all around the mound. It's like a very distinctive layer on Mount Sharp. And we were very curious how it formed and what it told us. This is what it looked like on the ground. It's called the boxwork structure. So you can see this is what those webs look like. It's these resistant ridges and then these more erosive hollows. And we were able to explore, look at the chemistry of the ridge and the hollows. Interestingly, we didn't find that much difference. It's very subtle, but all you need is a little bit of a subtle difference in the hardness of a rock and billions of years of a feather duster of the Martian atmosphere, and it makes a very dramatic change. We found these weren't salty. They're actually clay-rich. The clays have returned. That's interesting. But here's a picture that's both artistic and scientific that shows our great feature of these features. This line you can see running down the middle, we found this was very characteristic of a lot of them. They had fractures running down their middle. And so we think these actually formed when we had groundwater coming up. We're now nearly 1 kilometer above the floor of Gale Crater, and we're seeing evidence of groundwater coming up this high and coming out and hardening the rocks around it, around these fractures where these rocks were relatively softer and eroded away. And so we're using this as a chance to study what groundwater on Mars was like, and the idea that you would have had water that would have been present well past the time that Mars dried up, extending the period when the planet could have been habitable. So if there was life on Mars, who knows how long it lasted on the surface, but it could have gone underground and perhaps persisted for even longer. We call these images our postcards. We've made a couple of these. They're actually taken with our black and white navigation cameras. And what we do is we take one image in the morning and one in the afternoon and the evening right before sunset, and we colorize them. So the morning image is in yellow here, and the evening image is in blue, and when you put them together, it makes just this beautiful artistic view. And there's the fracture, so you can see it. So what are we up to today? Well, we're continuing, we've wrapped up at this box work, we're continuing to climb through the sulfur-bearing units, magnesium sulfate-bearing units. And these are the kind of rocks that we're looking at now, and they're just wild. I wrote a mission update blog post about them a couple weeks ago that got picked up by the media, so maybe you read about dragon scale textures on Mars. That's what they call them. They're kind of these polygonal features. This is what it looks like up close. This is some of these polygons in the workspace. You can see the rover here. I mean, they're like all over. They're wild. They're so cool. They're weird looking. So we're studying them to figure out what the heck are these things. You know, we have ideas. Are they cracks that formed as the rock dried up and shrank? Are they similar to the boxworks where you had fractures and then groundwater coming up and cementing themselves? Why do they fracture in this kind of polygon-like powder? You know, stay tuned. We're working on it. We're exploring, we're discovering. That is what's so fun about being able to be on these missions is even after 13 years, you know, we're climbing higher, we're looking at different periods of Mars's history, and we're just seeing so many new and unexpected things. So I'll end with this picture of the road ahead. As we make our way up through the sulfate unit, we'll get towards the top of Mount Sharp, which again looks completely different. This is the youngest rocks that we'll be able to see on the top of the mountain. They form these dramatic features we call yardings. They're kind of like the bows of ships that have been sculpted by the wind. Nobody knows what they are. Maybe they're dust deposits from volcanoes. I don't know. We'll get there, we'll find out, and this is going to complete our traverse of this sedimentary section, one of the key sedimentary sections on Mars, and it's really providing us a huge strip chart of Martian history through this very interesting period of change. We found Mars was wet, then it became less wet, but then wet again, but then less wet, but then wet again. It was this periodic pulses of groundwater coming up, forming lakes, drying up, forming lakes, drying up, forming groundwater features that persisted through time. So, okay, I lied. This is my last picture. This is looking back with our beautiful navigation cameras again. It's a wonderful place. It's been a wonderful time exploring. Thank you all so much for your attention. I really appreciate it.
Dr. Abigail, that's just the beginning. These people have questions you're not going to believe. I'm going to let you pick the raised hand, and if you want the microphone, let me know. I'll come and bring it to you. It helps because we record these shows for YouTube. And otherwise, just yell out your question and good, I thought she was leading us, thank God. Something I said. So who's got the first question?
I see a very enthusiastic hand up front.
I have two questions. Is the composition of Martian clouds similar to the Earth clouds, or are they?
Yeah, so the clouds on Mars, the question is their composition similar or different? Some of them are water ice, some of them are carbon dioxide. We think these ones, the ones that I showed, are high enough that they're actually frozen carbon dioxide.
My second question is, what is the source of energy for the driving the
The question is, what is the source of energy? This is a perfect picture to answer that question. You may have seen other Mars rovers that have solar panels and then they get covered by dust, but here, you'll see in the backside of the rover, this is something called a radioisotope thermal generator, RTG. In here is a chunk of plutonium-238 that as it decays, it puts off heat, and we can use the heat to make energy that powers the battery that we run off of. So it's a great energy source. We don't care if it's dusty or sunny outside. It does have a finite lifetime, so in a couple years from now, probably it's going to get harder and harder to operate as the plutonium decays. But we needed a different source for this rover because of this experiment we have inside the rover. It needs so much power to detect these organic molecules.
What's the microphone? Well, just yell it out.
Yeah.
Okay, yeah, a couple of questions. The lapping water pattern that you saw, that was, I think you said it was 3 inches or 3 feet deep?
3 feet, we think.
All right,
Or
3 feet deep, but it's fairly high in the rocks. On Earth, you think, oh, it's been uplifted, some sort of tectonic uplift, not going on. But there is, and the area around it shows no current structure that would hold water of that size. So that's a puzzle. You've got all these little peaks, erosion between them. All right, so that's one question. The other is, if the water is being driven up through these crevices, doesn't that imply, or does it imply that there's a source of heat beneath that's driving that up? I'm new to all this, but I wondered.
Yeah, no, those are great questions. You're a budding hydrologist. Yeah, so the first question was about what's the geometry of the lake? You know, the rocks we see now are just kind of chunks here and there. We think probably once the crater was fully filled, and so you would have had a lake that was filling the crater, and through time what erosion has done is gotten rid of a bunch of those rocks, and so that's what's making kind of the strange shape that we see today. That's what we think. In terms of the groundwater, one of the awesome things that I didn't mention about Gale Crater is it's a really, really deep hole in the ground. It's one of the deepest holes for miles and miles around. So any water that you would have had, either through rain or snowmelt, would have kind of flowed down through Gale Crater. What caused the water table to rise and lower over time? It could have been just more or less input of water, that you would have the groundwater table coming up and down. You know, we talk about the groundwater table here in California. When we take too much away, it gets low, but we can have more input. But yeah, was there a source of heat that was also driving that? Maybe. Certainly when the crater was made, big hole in the ground, you definitely make a lot of heat when you make that crater. Question? Yeah.
I know you mentioned that the battery obviously has a finite life. Is there any vague idea, should it make it to the top of this mountain, to turn it around and drive it somewhere else, or leave it where it is as a monitoring?
Yeah, no, we're definitely going to leave it when it ends where it is. We are probably not going to make it all the way to the very tippy top of the mountain, but we think we'll make it high enough that we can touch and sample that layer. And then, yeah, what next? We have to figure it out. There's some cool stuff actually at the head of the Geddes Vallis channel from orbit. There's like hints that there's some really cool geology in there, so that's where I want to go and check that out. But yeah, we'll see. But yeah, eventually either the power will run out and we just don't have enough to even operate the rover, or funding will run out, or something will break on the rover, like the computer will fry, who knows, and then when that happens, that'll be the end of the mission. I'll go to this side.
What was driving the pulses in the levels of water that you said caused the
That's a great question. I would like to know. I think this is one of the, you know, the kind of good things about missions is they find things that then make a whole bunch of new questions. So to me, that's one of the big questions that this mission has opened up is what caused those pulses. You know, I mentioned it could be different availabilities of water. Maybe you had periods where you just had more snow melts coming down from the high latitudes of Mars that were feeding the groundwater table. You could model the environment to see if that's what's happened, but that's just a guess. I think this is one of the big areas that people might start researching because of what we're finding. Yeah.
What is the temperature here right now when it's take this picture, do you know?
Oh, good question. I don't know. We do have a weather station on the rover that's every hour takes the air and the ground temperature. You can look it up online. If you look at, there's like a Mars weather station. I know in the summertime, the air temperature or the ground temperature can actually get quite warm, like above freezing, but it gets down to like minus 200 at night. Yeah.
Two questions. What was the planned lifespan of this rover? And the other is there a sequel? Are we going to have another rover to replace it?
Great question. So this rover was warranted, like the warranty was for 2 years. Everyone hoped it would last longer. So we're definitely past our lifespan. I don't know how long it's going to last. There is a sequel rover that's on Mars called the Perseverance rover. Perseverance is supposed to answer the next question. So Curiosity is designed to look for signs of habitability. Perseverance is now, okay, we know Mars was habitable, let's go find the life. And it's doing that in two ways. First, through the instruments it actually has the ability to maybe detect signs of life in the rock themselves, but more importantly, it's collecting rocks that we think are promising for potentially having life. And the hope is one day we'll be able to go and bring those rocks back to Earth, where we can put the full weight of our Earth-like laboratories to investigate them.
So we're not going to send any more rovers up right
So there's a plan that was announced 3 weeks ago to send more helicopters, 3 helicopters, a mission called Skyfall, that will land in the northern part of Mars where we might have humans one day and take a bunch of pictures and look for buried ice. But my dream is to see fleets of rovers all over the surface. So. Yeah.
And just a technical question, how is all the information sent or transmitted to Earth?
Yeah, so the question is, how do we get the data back from the rover? I showed you a lot of pictures. You can imagine we collect a lot of data. Actually, this is another good picture. We have several antennas that we use on the rover that we can talk to and from Earth. We have this antenna here that we can actually use to point. This one is an omnidirectional antenna. Both of these can talk to Earth directly. And then this antenna back here is what we use the most to talk to orbiters. And we send data up through the orbiters that are orbiting Mars. And they have much bigger antennas, so they can send back much higher amounts of data than we could if we directly talked to Earth. Yeah.
What uplifted Mount Sharp? I mean, the crater was there first, laid all the layers down, and then you have Mount Sharp was like pushed up, or was that a rebound effect from the original?
Yeah, so you do, in impact craters, you'll get something called a central peak.
Right.
That is a rebound that happens when the crater form. If you look on the moon, some of the big craters, you'll see the mountains in the middle of the crater. We think Gale Crater does have a central peak, but we think this mountain is actually rocks that were brought in after the crater formed that have plastered themselves around the central peak. So this is a much later phenomenon. Again, we think the crater was maybe once completely filled with lakes and rivers, and then what you had is and sand sheets, the wind coming in and carving out, and it's kind of carved like a moat all the way around, and that's what's left it in the shape of a mound. And we see craters filled with mounds all over Mars. This is one of the more dramatic examples, but we see them all over Mars. They tend to form, there's like a series of progressions of how they fill out. They end up in these kind of croissant shapes in the middle of the crater, and that's what Gale Crater has. Yeah?
Are we still seeing methane? Seasonal methane?
Yeah, the methane question.
Yeah, I love that.
Controversial. Yes, so when Curiosity, right before it landed, there was a big announcement that we detected methane in the Martian atmosphere, and that was exciting because methane can be produced through geology when you have water interacting with rocks, but it can also be produced by biology. We landed, first we didn't find methane, but then we changed the way we did the experiments, and we actually were able to enrich the Martian atmosphere, and then we did detect methane, and what we found with the rover was that there was a seasonal variance of methane, where in the summertime, I think it was the summer there's more, in the winter there's less. I may have been flipped. Occasionally we get these like crazy spikes that happen of just plumes of methane going by. There's now an orbiter that's looking for methane, and it didn't find any, so that led to some controversy. But we think what happens, and why we're seeing with Curiosity not from orbit, is we make our measurements at night when the atmosphere collapses and traps methane close to the ground. And so it's at a concentration that's big enough that we can sense it, but during the daytime when the orbiter makes its observations, it's all throughout the whole atmospheric column, so it's much harder to detect. So yes, we're still seeing the seasonal methane. I think it's very real. It is puzzling how you can have methane like this and these spikes and not have it building and building. So there's got to be some mechanism that's destroying it that we don't fully understand. And we don't fully understand the source. Where is it coming from? So again, we found some things that are opening new questions. Yeah?
So those 5 or 6 really discrete little hills, the little curved hills, have you figured out what caused those? Air, water, volcanic activity?
Yeah, those hills through the past, those were probably ancient sand dunes. We can see something in them called big cross bedding, and we can see that it was like tens of meters of scale and size. And so that's, again, like go out to the desert, see these big dune fields. Those are the kind of rocks that that makes.
And then what is it that looks like it had that structure on the Curiosity that has that nice rivet pattern? Or
Oh,
rivet pattern?
This?
That.
Yes. So this is part of the rocker bogie system. This is what the wheels are connected to. So there's 3 wheels on this side, 3 wheels on that side. This is the differential. I think that's the differential. As the wheels turn, it can go like this. And so that's how we can steer side to side.
Perfect, thanks.
Yeah.
Other than the thickness of the rock blocking the radiation, what are some other things that you've learned that would help like astronauts on Mars? And also, have we thought of it as harder than previously for astronauts to be there, or easier based on what we know?
Ooh. I'll answer your first part of your question first. Another one of the findings that I think is really cool is, as I mentioned, we've been able to measure the radiation through the full solar cycle, so we can see how it changes as the sun is more active and less active, like with the number of sunspots. It turns out when the sun is more active, that tends to block a lot of the galactic radiation that's coming to the surface, except when there's a giant solar flare. So if you all remember, I think it was last year or early this year, there was that huge flare that came, and like everybody everywhere saw the aurora, and it was all over the internet. That same flare, not that same event, but that same sunspot set up another flare a little bit later, pointed directly at Mars. And so we saw the biggest spike we've ever seen in the radiation on Mars associated with that same really active event, and it was equivalent to 30 chest x-rays. So if you were on the surface, that's the kind of radiation you would be receiving. So that would be a good time to get inside. In terms of how it's changed our thinking about how hard or easy it is, I'm not actually sure. We've certainly learned a lot that have improved our models. I haven't heard anything that we found that it's dramatically different than we expected. So I think I'd imagine it's kind of similar to what we expected, but now we have less uncertainty associated with it.
Can I add one part to that? Wait, now I'm forgetting. Wait, sorry, come back to me.
Okay. Other questions? Yes?
Why is Mars red?
Why is Mars red? Because it's rusted. So we think Mars is a very iron-rich planet, and there's a lot of iron in the rocks, and it's a very oxidizing environment right now on the surface, and they have oxidized. So it's all this ferric iron that you have that forms dust, and that's red. We think there's all kind of like, the minerals are like goethite and hematite and nanophase iron oxide is what makes it red.
Where did the free oxygen come from to rust the iron?
Where did it come from? I mean, there's still a little bit of oxygen in the atmosphere, and I think over millions of years. Yeah, not a lot, but a little bit.
I thought it took light to make free oxygen.
No.
Like photosynthesis.
No, I don't think so.
You want one here? Did you see the movie Martian, and did you like it?
Yeah, you can look that up on the internet. Check me if I'm wrong. Yes, did I see the movie The Martian? I did, and yes, I loved it. The most unrealistic thing on the movie, I know they talk about like, oh, the wind wouldn't have been strong enough to tip over. Sure, that's a good narrative device. You need that to start the plot. It's the ease at which the intergovernment agencies were able to work together. And how nice the offices at JPL is. That's yeah.
Could you explain a little bit more about the data transmission and that antenna use a great volume to the orbiters, but then these two antennas go directly to Earth. How do you decide what goes where?
Yeah, so a lot of the times when we uplink, we usually do the direct to Earth. We'll send our plans directly from Earth. They're not very large amounts of data, but when we want to send a lot of data back to Earth, we'll do it through the orbiters, like all of our pictures and science data that we collect.
Does that include navigation?
Yeah, so the commands that we put to drive the rovers, those are coming from Earth. Yeah.
Are there seismometers on the rover, and are you able to correlate, if there are seismometers, are you able to correlate between Curiosity and Perseverance? Any Mars quakes or any activity?
Yeah, that would be cool. Unfortunately, there's no seismometers on these, but we have landed a seismometer on Mars. It was the InSight mission. It actually launched out of Vandenberg, the only interplanetary mission to launch out of the West Coast. It had just one seismometer, but the geophysicists are geniuses, and they were able to figure out how even with one seismometer, you could get a pretty good sense about where earthquakes were coming from, or Mars quakes. And yeah, they actually did detect quite a few number of Mars quakes, some from impacts, but there's a bunch that they actually found clustered in one area of the planet called Cerberus Fossae. And so it's puzzling, why is that area particularly active? Again, you learn things and then you get new questions.
How
far does Curiosity go in a day? And sort of combined with that, you just mentioned that the cues and commands are coming from here. To what extent does it have the ability to do thinking on the spot? And then just a speculative question for you to think about, for you to give us your ideas. To what extent do you think rovers in the future would benefit from doing some of their own thinking versus us doing it and sending?
This is a hot topic right now.
Within the context of like geology and direction and things like that.
Yeah, AI solves everything. No, and I'm serious, it is a big area of excitement for everyone thinking about, obviously AI has seemed to me this like sudden huge leap, and how can we use that? So our rovers do have onboard smarts. How far we drive depends on the terrain and how much we want to use these onboard smarts. So if we drive for only to where we can see, we usually drive 30 to 50 meters. We also have the ability to use a capability of autonomous navigation, which lets the rover just pick its own path, and we have different flavors of fear that we can program into that. Perseverance, the other rover, actually, if you look at the total distance, it's been on Mars a lot less time, but it's gone way further because it has more capable processing, and so they use that onboard autonomy a lot more to drive really far. I think they have the record now, like a 400-meter drive in a single, uplinked plan. So we do have autonomy on the rover to do that. Because Mars is far enough away, it takes 15 to 30 minutes for a signal to get there. And then, as I mentioned, we mostly talk through the orbiters, so you got to wait for just the right time when the orbiter goes overhead. So we don't joystick them real time. But yeah, in the future, can we make rovers more autonomous? I'll say it has certainly been proposed. There's a difference between if you're doing the thing or if you're into the technology to do the thing. So I think a lot of engineers would love to see the autonomous geologist where you just hit go and it knows what rocks to go to and what data to collect. As a geologist, I'm like, I don't know about that. It's kind of an art. It's kind of the things where you learn by seeing, and it's hard to discretize how you do that. So we'll see. There was a study that we did a couple years ago where they had a really nice model where you hit go for like a week or two and the rover would pick what data to collect, but then the scientists would come back and say, oh yeah, that's really interesting, let's go back and do more, let's get that. So I think maybe that blend of autonomous technology and actual humans looking at it is the best way to go, but we'll see. Yeah?
How many scientists do you have working with you on this mission, and what are the different ranges of science being done? Is it all in-house? Is there anything that you get questions from outside that come to JPL?
I love that question. I don't think anyone's ever asked me that. And the answer is we have almost 400 people on our science team, and they're spread all over the world. There's only a few of us actually at JPL. A lot of them are university professors in the US, and then of course outside the US we have a lot of scientists from France, Spain, all over the place. And the specialties are all over the place, as you imagine. This mission is doing so much. We have organic geochemists, we have geologists, we have mineralogists, sedimentologists, we have weather experts who are studying the environment, the radiation physicists, and it really takes all of these people and all of these expertise to put together a coherent story. Yeah, in the back.
Yeah, do you have a sense of the approximate cost per year for this mission?
Oh, cost per year of the mission. Well, when it was built, it cost $2.5 billion to build this rover and send it successfully to Mars. Right now, our operating costs are around $35 million a year, $40 million a year. And they go down every year, which sometimes limits what we can do with the rover, but we're constantly trying to figure out how to do it cheaper and cheaper as well.
Thank you.
Yes?
Is there a current plan to retrieve the samples?
Yeah, is there a plan to retrieve the samples? Perseverance has collected a whole bunch of samples, and we did have a plan, but it was too expensive, and so NASA said go back and do better and come up with another plan, and so a whole bunch of proposals were put in, and I think they're thinking about those proposals, so we're going to have to wait and see if they decide to go forward, and if so, with what proposal. I sure hope so, because the science is really cool.
Well, Dr. Abbey, we've been known to get presidential questions from our captain of the club. Do you have anything you want to ask, Jerry?
Several questions were asked already.
Let me give you
about the dust and stuff that you get on Mars. I know on the moon, the dust is very damaging to equipment because it's sharp. But I don't think it would be sharp on Mars with the wind blowing it around and rounding everything off. But do you know of any problems that they're encountering with toxicity of dust or wind-blown dust getting in things that will affect equipment?
Yeah, you're absolutely right. On the moon, the dust is mostly made by impacts, and it's just very angular. On Mars, it's been rounded off probably, but yes, we don't exactly know precisely what's in the dust. Is it toxic? We found there's a lot of perchlorates in some of the things, which is pretty toxic. So this is one of the major concerns if we want to send humans to Mars. How big of a problem is it, and how much do we need to mitigate it? I'd argue this is another reason to bring samples back so we can really figure this out. In terms of the rovers, dust isn't really much of a problem. It hasn't gummed up any of our mechanisms. They're pretty well sealed. There's maybe there's some dust on our lenses, but that's not hindering what we can do with them.
Also, can you estimate how much regolith it would take to shield an astronaut on Mars from radiation to a safe level?
I can't off the top of my head, but I guarantee you people have. So I would need to look that up.
Thank you. Excellent talk.
Here's my silly question, Dr. Abby, as I climb the stairs. In my opening remarks on your background, I mentioned something about Phobos, one of those little dinky, they're like asteroids, not even moons. What are you doing with them?
Yeah, I was hoping someone would ask. That's why I put that in there. Yeah, so the moons of Mars are super weird. They look like potatoes. There's 2 of them. And they're one of the great mysteries of planetary science because we have no idea what the heck they are. They could be captured asteroids. They really look like asteroids. But then it's really hard to explain their orbits if they're captured asteroids. They're both very circular and planar. One is spiraling in, one is spiraling out. Like, what are the odds that you capture an asteroid in those orbits? And in that sense, it makes much more sense that they would actually be created by an impact that threw debris into the air, formed a ring around the planet, maybe like our own moon. But this mission that's launching October of this year, led by JAXA, there's a NASA-contributed instrument on it, is going to go to the moons and measure their composition really well and bring a sample back. And it's a great, hopefully easy to test. Is it a chunk of Mars or a chunk of meteorite? And hopefully we'll be able to find out. So I can't wait to know. I really want to know. So stay tuned.
It's possible they could be asteroids?
Yeah, so if it's an asteroid, it'll look like meteorites that we have here on Earth.
Wow.
Or it'll be something completely different, and then we'll have to start all over again, which seems to be how things go. So, I don't know.
I'm thinking they don't have enough gravity to hold a rover, though, do they?
They have just enough. They're actually going to deploy this little tiny rover built by Germany. It's called Idifax. It's really cute. It's going to kind of like bounce. It's like a box, and then it sort of unfurls itself. And yeah, we'll see how it works. We'll see.
But Phobos first and then Deimos later?
Just Phobos, so it's going to orbit Phobos for a bit, map it, and then we're going to pick a spot where we're going to land, grab a sample, and then fly by Deimos on the way back to Earth to return that chunk of Phobos. And on that first landing, grab a sample, we're going to pop out the rover to do some extra science.
So you're going to be down there in JPL for a while.
I hope so.
Have you ever considered, do you have a pipe dream of being a university professor lecturing? Because you do a good speech, a good presentation.
I love being at JPL because you're with the engineers working on the missions, and I really love that. But that's why I love invitations to come share my excitement with everybody.
I got to tell you, if you're going to launch more little helicopters, Kakin is his last name. What's his first name? Martin Kakin. Look for him. C-A-I-C-A-N. He spoke to us last summer. I believe it was last summer, right, July? He was right on this stage, and he took us there with a little whirlybird. You did good, Dr. Abigail. Since we know you wouldn't be able to come to meetings, so we're not going to induct you into the club, but this is as close as we can get. Official one.
Thank you so much. see that and I was like, that looks cool. Oh, that's so exciting. Thank you so much. Oh, wow. Thank you so much.
Isabel, Abigail, we're gonna have you back. Next time something big happens, let us know, all right?
Okay.
Okay, folks, listen, thank you very much. You want to come up and close the meeting? I'm going to tell you, we've got a half hour, you know, we're going to be out of here. But if you want to socialize, be my guest, or you want to talk to Abigail, come on up. The forms to join the club, and then bring your favorite casserole next month to this very room are up here. Thank you for coming on behalf. We're going to officially close the meeting with the president.
This meeting is closed. I can't jump up on the stage, I have to use the stairs.
You wouldn't have done it.